Welcome everyone back to geomorphology. Right now I want to talk to you a little bit more about geomorphology tools, the tools that geomorphologists use. Now remember, in our first set of videos we talked really about how we quantify the morphology of the surface of the Earth. We talked about how we can characterize and create three-dimensional models of the Earth's surface. We talked about getting elevation in terms of absolute elevation from sea level, but we also talked about relative changes of Earth as well. So that first set of lectures was really set on our ability to, kind of identify and characterize landforms. Now we're going to move on to another really important part of geomorphology, and that's being able to put some time controls on when landforms have been created and how long it took them to be created. So this is going to be about the dating methods we use in geomorphology to date the creation of landforms and to quantify how rapidly the surface of the Earth is changing. So that's our goal here today. And so behind me here, the picture right here, this is me a few years back working in a radiocarbon dating facility at the University of Arizona, where I had collected small bits of wood from river floodplain and river terrace deposits. And if we can date that wood, then we can use that to start to understand and date river processes and understand how rivers have changed over time. So what this whole line is behind me here is this is designed so that we can capture the carbon within the wood. And how we do that is we start way over here at the beginning of this thing, and we put the wood into this vacuum chamber and we burn it, and then we create carbon dioxide. And then this whole line here is basically trying to isolate the carbon dioxide from other gases that are created when you burn the wood. And over here at the end of this, I've actually isolated the carbon dioxide. I've frozen it in liquid nitrogen here. And now I am sealing off the test tube with a torch here so that we can take that carbon and turn it to graphite so that we can actually determine the radiocarbon age of that wood. So that's just one example of a dating method, and we're going to talk about a few more of these as we go through this lecture. Okay, probably the simplest way we can talk about the kind of quantifying time is through relative dating methods. You probably learned about relative dating methods in an introductory geology class. You might have heard them called Steno's laws, but just one in particular that we use in geomorphology would be the law of superposition. That the layers on the bottom are older than the layers on the top. And so a specific example in our world would be we could have essentially a till deposit, and then that till deposit is overlain by lake sediments. We know that till deposits are deposited by glaciers, right? That a glacier dumps out a bunch of coarse-grained and fine-grained sediment all at once, and then lake sediments are deposited at the bottom of a lake. So in this location, we know that a glacier came first, dumped off a bunch of till, that glacier receded, and then we had a lake that was in this location, and we deposited lake sediments. So relative dating, in this case, glaciers first, lake second. There's some other relative dating techniques we can use. This here would be looking at moraines. So moraines are the landform often associated with glacial till. And so here, the glacier dumps off right here, the glacier would extend down here. This might be better for me to actually draw. Try and draw it here. Okay, so I can use the pen here. That at one point we had a glacier that it came all the way around here and deposited this outer moraine. And then we have these nested younger moraines that represent younger and younger recessions of the glacier itself. So again, these would be our way of having kind of a relative age. Another thing we can talk about when we talk about kind of the relative ages is like the basically how rounded a landform is. This younger moraine on the bottom here is very sharp crested, right? Very sharp crested. The glacier recently receded, and we basically have this steep pile of sediment. Whereas on this rounded moraine crest that we're looking at right here, in this case, we started off with a steep crested moraine, and over time we've had mass movements, little mass movements on the side that have rounded off that crest. So these are both relative techniques we use to determine the relative age of geologic events. Another example of that would be looking at fault scarps. We talked about fault scarps in the Big Sink lab, and so a fault scarp will start off as a very, very steep a steep feature in the landscape, with dramatic relief right on it, because again, remember with a fault, you immediately all at once get a dramatic change in the relief, and then over time you're going to have weathering processes that round that surface. So we start steep here, and then we round that crest over time. And so here's a very young fault scarp here, and then here's an older fault scarp. This is the Hebgen Lake earthquake in Montana, and this fault scarp here is from the 1950s, and we can see it's sloughed off as we've had sediment that's kind of fallen off the fault scarp and kind of rounded that crest. So again, we can put a relative age on these fault scarps just on their morphology. Okay, another thing we can think about is kind of how dissected and eroded a geomorphic landform is. So behind us, we have a cinder cone. Oh, sorry. Behind us, we have a cinder cone here. And this is a relatively young cinder cone. This is in the Owens River Valley. This was one of my Mojave classes that we came down here and checked this out. And so this is a very fresh looking cinder cone. Look at that. It's nice and smooth. You can imagine that just recently this thing was built up by the ejection of pyroclastic material out of the cinder cone. Compare that to this very, very old and highly dissected cinder cone. Now, when I say dissected, what I'm talking about are these channels. You see right here, these are erosional channels along the cinder cone, and that's occurred because that cinder cone is very old, and there's been time for other fluvial processes to erode these deep, deep channels in this very old cinder cone. Okay, another relative dating technique would be just looking at weathering rinds. So weathering rinds, imagine you've got a boulder. Oh, I've got one right here. Oh boy, that's a big one. Check out this boulder. Everyone see this? Okay, so this is a boulder. It's a rounded boulder. Let's say you have this that was deposited in a river, and then what happens is this was part of the river channel, and then the river incisors and cut down, and it abandons that old river channel, and so that becomes a river terrace. And then what happens is that boulder is then susceptible to weathering, and so what happens is it'll weather more on the outside and then progressively weather in. So a relatively fresh young river terrace would have a very small weathering rind compared to, say, a much older river terrace where there's been significant amounts of time for weathering. So here again, you start with the weathering at the surface, and then it goes in, weathers in. Okay, sorry about that. We had the video cut out for a second, but we're back, and we were talking about these weathering rinds on this boulder, and this is a relative dating technique where we have essentially weathering that starts at the surface of the boulder and then progresses into the boulder over time. And so the thicker the weathering rind, the more time there has been. Okay. Click in here. Okay, another relative dating technique is using rock varnish. So rock varnish is this black material that develops. It's a manganese oxide coating that develops on rocks in arid regions, in deserts. And so the longer that a boulder, a rock, a bedrock surface is sitting at the surface of the earth, it'll develop a thicker and thicker rock varnish rind and get darker and darker in color. This is a great example here on this alluvial fan. So here are the mountains here behind us, and they're dumping out the sediment, building up this big, thick alluvial fan. And right here, notice this darker surface versus this lighter surface. These are telling us relative ages on the alluvial fan. Right here, this area in black, that's an older part of the alluvial fan. The alluvial fan filled up, and that older part of the fan stabilized, and then something happened. There was a change in the system, and the alluvial fan is now incising and cutting down in. We have a younger surface here, and you can see a couple of places where we have this younger, whiter material as the fan filled up, and now we're cutting down into it. So relative dating using that rock varnish. Okay, we can also have a calibrated relative age. And so this is going to be basically, we're going to take relative ages, but then we're going to try and put numbers on them. So we can do this using things like, say, lichens. So, okay, a lichen grows on a boulder, and lichens generally get larger over time. So if you have a fresh moraine that dumps out a bunch of boulders, the bigger the moraines are on the boulder, the longer they've been there. Does that make sense to everyone? And so if you can kind of create kind of a calibration of how quickly lichens grow, then you can start to say something about the age of that surface. So that's why we call this calibrated. For this idea of calibrated ages with lichens is called lichenometry. And essentially how this works is you basically find lichens of a certain size, and then you find them on a surface with a known age. Well, how do you find a surface with a known age? Haha. There we go. Go to a graveyard, right? We know that these tombstones, these headstones will have ages on them. And that can tell us that, say, okay, this tombstone was put out in, there we go, put out in 1650 versus a tombstone that's only been out in the graveyard since 1850. And what we do is we go and we measure the size of the lichens. And so this y-axis here is larger and larger lichens. Okay? And so, so here, if we go up on the y-axis, those are bigger lichens. And as we go to the right on the x-axis, that is greater back in time. And so we can use that. We can go out, once we've created our lichen growth curve, you can go out and measure a lichen and say you found a lichen that is 60 millimeters in diameter. You can go over to your lichen curve and measure down and estimate that maybe that lichen was colonized that surface in, let's say, 1740 or 1730. So that would be a calibrated technique. Okay, whew. So those are relative age dating techniques we use in geology and specifically in geomorphology. Okay, now we're going to move on. We're going to go on to numerical dating techniques where we can put absolute ages on some sort of geologic event or a landform. Now here I've put on for our first slide here the second step in that radiocarbon process. Do you remember the first step was recreated carbon dioxide gas, and once we have that gas, we put it into this machine that can convert that gas into graphite, pure carbon, that then we can actually put in a particle accelerator and count the atoms of carbon-14 in them. So we'll get to that here in a second. But let's start off with some more simple numerical ages, ways we can get numerical ages, and that would be tree rings. This works really well because we know that trees grow one ring per year. So if we have a new surface, so here we've got, let's say, a moraine, a young moraine, and a tree gets established on that moraine, we can essentially count the number of rings to determine when that moraine was deposited and when the tree got established on that moraine. So the older the surface, the more trees you're going to have, the bigger trees you're going to have, and you're going to be able to count those rings. So here's an example of how we collect those tree rings. We use a tree corer, where we core into the center of the tree. This is Seisha, who did a tree coring project for geomorphology a few years back up in the Blue Mountains. And so you core in, and then you kind of extract your tree core. And then once you have your tree core, you bring it back to the lab, and you painstakingly measure every single ring width. Does that make sense? Every single ring width. So you can date a surface. Now the center of the tree, that's the oldest, and then it gets progressively younger as we go out. Now here's a really cool thing about trees. We can use trees and tree rings not just to establish the timing of when a surface became stable and the trees colonized that surface. We can also use trees and tree rings to tell us a little something about paleoclimate. And that's because the width of the ring is dependent or is influenced by two things: how old the tree is, and also the conditions during that growing year. So let's say it's a really, really wet year, the tree's really happy, it's going to put on a thick ring. But if it's a really dry year, the tree doesn't grow very much, it puts on a thin ring. And so we have these two things that influence the ring width. So look here, notice how in the center of this tree, I can do it this way right here. Notice in the center of the tree right here, these rings are generally thicker. That's because the rings when the tree is youngest are thickest, and they just get thinner over time. So if we can account for that, if we can create what's called a growth curve. So here's a growth curve where the thickest rings are the youngest. So this is looking at ring thickness over time from young to old, from thin to thick. If we can account for that thickness, then any deviation, years when that ring is thicker than that versus years when that ring is thinner than that, can tell us whether it's dry or wet. So then we go ahead and we detrend, we subtract out that curve. So that's what we're showing right here. We take the rings, we detrend them, we remove that growth trend, and then we can just look at wet years versus dry years. So this is a very important technique we use. Okay, moving on, another thing we can do with trees and any other living material, whether it be bones or something else, is we can use radiocarbon dating. And radiocarbon dating is great. Radiocarbon dating allows us to determine the age at which something died, right? And so how does radiocarbon dating work? Well, it starts way up in the upper atmosphere, right up here, okay? And what happens is we have some cosmic radiation that comes in from deep space, and it runs into a nitrogen atom in the atmosphere. Plenty of nitrogen up in the atmosphere. That causes a radioactive decay and the production of carbon-14, an unstable radioactive element of isotope, of carbon. That carbon is then oxidized and creates carbon dioxide in the atmosphere. And then what happens is that carbon dioxide is then taken into the plant through photosynthesis to create things like wood and leaves. So now you've got two types of carbon that are going into the plant, right? You've got the stable carbon, the carbon-12, and then this hot carbon, this radioactive carbon, the carbon-14. And so as long as that plant is alive, right here, it's bringing in fresh amounts of carbon-14. But the second that that organism, that tree dies, it's no longer bringing in new carbon-14. And what happens is it's a radioactive isotope, and so it decays away over time. And so the longer something's been dead, the less carbon-14 it's going to have. And the rate at which it declines is called the half-life of the isotope. So the half-life for carbon-14, that half-life is 5,730 years. 5,730 years. So that means that once this tree dies, let's say you've got some wood down here that we're interested in the trunk of that tree. If that dead tree has been in the landscape just sitting on the surface for 5,000 years, it's going to have roughly the half the amount of carbon-14 that it started with. And so after 4 half-lives, we're going to be down to 1/16 of the remaining carbon-14, and that tree is going to be out in the landscape dead for over 22,000 years. So that's the basics of how radiocarbon dating works. We'll be doing a lab on radiocarbon dating towards the end of the semester. Okay, so the other really critical aspect of carbon-14 dating is, again, we might not necessarily care about when the tree died. We care about some sort of river process. So the river here, right here, the river here, this is a river terrace. And as everyone see right here, we've got a giant tree trunk in the river. And so this tree trunk, when we use radiocarbon dating, it's going to date the age of that tree trunk, but we're going to use that as roughly the age at when this river terrace, this river deposited this terrace. Okay, there's some other really cool numerical techniques that are kind of relatively new in the field of geomorphology and are really, really exciting. Thinking about your next steps, going to places like graduate school in geology, there's lots and lots of projects that use these techniques. So I want to talk about 2 of them in particular. The first is what we call luminescence dating. Luminescence dating. Another term you might have heard is optically stimulated luminescence. So luminescence dating is a way that we can determine how long grains of quartz or feldspar have been buried from the surface. So how does this work? Well, we start with a beautiful quartz grain here. Beautiful quartz grain that's sitting at the surface. And what happens is that grain is just sitting there at the surface, and it's cleaning out any of these OSL traps. And so as soon as that grain gets buried, there's going to be radioactive decay in those sediments. And what happens is, now that we have radioactive decay going on, what happens is these little imperfections in the crystal lattice of the quartz grain, they're going to start to fill up with electrons associated with that radioactive decay. And the longer this grain has been sitting here, the more of those electrons you're going to have trapped. And we know basically how quickly those electrons start to accumulate in a sand grain. And so we can use that to tell us how long that grain has been buried. The cool thing about OSL is that a grain can go through multiple cycles of getting buried and then being exposed again at the surface, where then those traps get cleaned out. And so the OSL technique dates the last time a grain has been buried. And so we call this a bleaching event. So we start here, we've got a signal that's accumulated in a quartz grain, and then we expose it to light. We flush out those traps, and then we bury that grain, and then slowly over time again, that grain will accumulate those electrons, and then we can come and we sample. Here's an OSL tube. You have to do this in the dark. You pound in a metal tube, and then we sample those grains, and then we can take these back to a lab and count the amount of electrons in there and determine how long that sediment's been buried. So this works really well for things like sand dunes, where you've got a sand dune that was moving and those grains all got bleached, and then the sand dune stabilizes, and you can go in and use the OSL technique to determine how long it's been stabilized. So this is optically stimulated luminescence. And these pictures are just 2 pictures of some sites where I've used OSL to constrain the age of landforms. Okay, another really cool technique that is used quite often in geomorphology is cosmogenic radionuclides. So cosmogenic radionuclides, right up here. You can think about this roughly, or one way to think about it is rocks getting a sunburn. So it's almost the opposite of OSL. OSL dated how long a quartz grain has been buried. Cosmogenic radionuclides tell us how long a rock has been exposed at the surface. So let's say we've got a quartz grain again here. We're going to get a bombardment of cosmic radiation coming in from deep space that bombards that quartz grain. And what it ends up doing is the oxygen in that quartz grain from the SiO2, we get a radioactive reaction, and we create beryllium-10. And so that beryllium-10 accumulates in the rock. And so the longer that rock's been at the surface, the more beryllium-10 it's going to have in it. And so this is a technique we use especially where we don't have any organic material for radiocarbon dating. So a great example would be places like glaciers and alpine systems where there's not a lot of organic material. So here we want to know when a glacier deposited this boulder. We can go out, we can whack off the outside of the boulder where we have lots and lots of those beryllium atoms in the rock. And this is kind of just showing how much beryllium accumulates. It's only right at the surface. As you go down into the rock, you don't have nearly as much beryllium. And so we just go down in and we sample that rock. We determine the amount of beryllium in it, and that can tell us how long that rock's been at the surface. So that's CRN, cosmogenic radionuclides, a really, really cool technique that we use to constrain the timing of geologic events. We can also use it for measuring rates of geomorphic change as well. That's the last part I'd like to talk about in today's video, is we've kind of talked about ways that we can use either relative or absolute dating techniques to constrain the age of a surface, but another critical aspect of geomorphology is our ability to measure rates of change in geomorphic systems. And so we're often interested in kind of how quickly something's eroding, how much sediment's moving out of a river. And so we've got methods we use to quantify those rates of change. So here, this picture here, we're looking at an outwash system associated with a glacier where we have large sediment loads that are being flushed out of this system. And we're using a total station here to kind of measure how the channel is changing over time. Okay, so there's different ways that we can quantify changes. One would be kind of thinking about a river, and we can think about a river over time. And so let's think about a river over time. And so here we can talk about kind of the river stage, so how much water is in the river over time. And so we can measure when we've got high stage and then low stage of the river. And then once we have the amount of water, we can convert that to how much water is in the river, which we call discharge. So we can convert from how high the river is, once we know the dimensions of the channel, to the discharge. And then once we calculate that discharge, then we can start thinking about, well, if we have a river of a certain stage, we know that it has a certain amount of water in it. Moving on from there, once we've kind of calculated that relationship, then we can start to think about how much sediment is in the water. And so we can quantify the amount of sediment. We can go out and sample the amount of sediment and look at, okay, at discharge of a certain size, as we get larger and larger discharges, we're going to have certain amounts of suspended sediment in that water. And so we can quantify that change, how the amount of sediment moving in water changes over time. Okay, so here's an example of that. We've got a site here where we've had construction on a site, and we might be putting extra sediment into the water. And so we can go out, whoop, tripping over the rock, my boulder from earlier. We can go out, we can sample the water and determine the amount of suspended sediment in the water, and look at kind of how that suspended sediment varies with time. Okay. Another way we can quantify rates of change is looking at things like trees and looking at the landscape themselves and combining some of our techniques. Check out this tree here. This is pretty interesting, isn't it? So here's our tree right here. What's going on down here? Trees don't generally grow with their roots above the surface of the earth, do they? No, we're looking at erosion of this surface. So what happened was this tree was growing like any other tree with the roots beneath the surface, and then we've had erosion, which has exposed those tree roots. And so we've seen a change in this system where we've had erosion, and we can use tree rings to date when this erosion happened, as trees don't like to be to have their roots exposed like this, and we'll be able to see that signal in the tree rings themselves. Okay, the last method I want to mention for kind of measuring rates of change is another really cool technique. that we use in geology and geomorphology, and that's cesium deposition. So cesium 137 is a radioactive element that was deposited in the atmosphere associated with above ground nuclear testing in the 1950s. And so we have what's called fallout of cesium-13 that is in the atmosphere. And so there was no cesium in the atmosphere prior to 1950, and then we do above ground nuclear testing, and we have a big spike. We ban we ban this type of testing, and that spike goes away. And so now we're not putting nearly as much cesium in the atmosphere, except for every once in a while when we have a radioactive catastrophe like Chernobyl. But this cesium spike here tells us it's basically a layer that we can now use in soils to quantify how rates have changed since 1950. And so what we're looking at here in this picture is we would have started with an original land surface, and then what happens is we deposit on top of it sediment that has lots of cesium in it. So we can quantify how quickly we're burying this surface since roughly 1950. And so that's another method we use to constrain rates of change at the Earth's surface. Great. Okay, that's all I have for you. Thank you for watching.